What's up, AP Calculus students? Mr. Ford here with a homework tutorial. You guys are like 3 weeks away from the end of high school or something, 4 weeks away. It's got to be cool. We're really close to the end of this class too, which is getting there. We're at 7.3.1. We just did our first lesson on what we're going to call the broader topic here is differential equations. Which is, if you go on to college math, you might find it to be like an entire class that you take. So this is a whole thing. But we're only going to look at kind of one or two different little methods that we do here in Calc AB. And really, we're going to get a chance to practice those right away in 7-100. So let's get into it. We'll probably end up doing 100 in class today. We'll see how the timing works out. But let's go ahead and dive right in. Now, for question A, for all these questions, I'm going to need a little more room here because they all require a little bit of space. We know that dy, dx, actually question A we can do right now because question A is just a simple antiderivative. If we're looking for dy, dx, all we're looking to do here is solve these equations for y. We want to know what original equation y has this derivative. So in this case, this is pretty easy. Y would just be 7x squared over 2 plus c. Just thinking about antiderivatives. If you took the derivative of 7x squared over 2, the 2 pops down, cancels out with the 1/2, bam, Bob's your uncle, you got 7x. So A, I don't have much to say about. B, however, is really at the heart of what we're doing here in chapter 7.3. So I'm going to make a spot for B all the way over here. This is for part B. We know that dy dx is equal to 7y. I'm also going to make a space for question C. We know that dy dx is equal to e to the negative y power, like that. Now the objective here, all these problems are kind of solved the same way. The objective is to gather the y and the dy on one side and the x on another side of the equation, and then be able to think about them separately. So we call this the separation of variables. So what I'm going to do is I'm going to multiply both sides of this equation by 1 over y. And I'm also going to multiply both sides by dx, which I'm going to write weirdly over there. And what that will do is it'll write the equation a little differently. How about 1 over y times dy equals 7x dx? Or not 7x, just 7. It's just 7 times dx. And now that we have the variables on the same side, what we're going to do is basically take the integral of both sides. One of those integrals is with respect to y, and the other one is with respect to x. The integral of 1 over y is natural log of the absolute value of y. And the integral of 7 with respect to x is going to be 7x plus c. Now, we could put a plus c on both sides. We'll get to that in the next question. But, since c is just a general constant variable, we just only write it on one side of the equation. Since they both have their own constant, you could subtract one constant over and combine it over here. Now you got a constant over there, but it's just a placeholder anyway. Now, this is a really common differential equation. And the next thing we're going to do is take e and raise it to the power of both sides. E to this, e to that. It's going to look like that. E to the natural log of y just becomes y, and this is e to the, in parentheses, 7x plus c power. A little bit of algebra goes like this, is we're going to have e to the constant power times e to the 7x power. And then since c is already just a general constant, the equation is y equals some capital C times e to the 7x. And there you go. Now, at this stage, we could, if we knew an initial condition, like a certain point on this, we could solve for that big capital C and give the exact equation. But we're just giving a general equation for this, and there you go. If you took the derivative of this, you would get back to the original 7y. All the constants would go away. That's kind of the way it works. Let's take a look at C also while we're here. Give me a second to pull up my, let's see, oh, okay, perfect. I'm just kind of pulling up my answer sheet. Usually I have that up on the other monitor so I know what I'm doing here. For this problem, I like to think about this as e to the negative y. I like to think about this as 1 over e to the y power. And I like that a lot because what I can do is I can separate the variables really easily by multiplying both sides by e to the y power. And so after separating, what we'll have is we'll have e to the y times dy equals dx just by itself, because I'll multiply both sides by dx also to get it out of the bottom. There, like that. And now we're going to take the integral of both sides, kind of like we practiced in class today, or what we did in the last problem, And this is really nice because the integral of e to the y is just going to be e to the y plus c, but we'll put the plus c on the other side. So we'll have e to the y over here equals x plus c over there. Perfect. And then all we're going to do to get y by itself, we're going to take the natural log of both sides, because that'll get the y out of the exponent, and y is going to equal natural log of x plus c, like that. And there is your general equation for that derivative right there, that differential equation. Pretty cool. Okay, let's take a look at the next question, which is kind of a good one to be aware of when you're solving problems like this. Nick and Rosa are arguing over who's right about solving this problem. I'm sending a verification code to myself to log in. Okay. Nick and Rosa are arguing over implicit integration. Nick thinks the constant of integration must be added in when you find the antiderivative. Rosa thinks that you add c later after you solve for y. Which student is correct and why? Give an example to justify your answer. I really want to think about question B here. 254505. I'm logging in over here on the other monitor too. I really want to look at our working question B. Nick thinks the constant of integration must be added when you find the antiderivative. So Nick is saying we found the antiderivative right here in this step, up here in question B, and we added the constant of integration right there. So we kind of did what Nick said we should do, which is why I'm leaning toward Nick. Rosa thinks that you can add the c later after you solve for y. Which student is correct and why? So Rosa is saying that we can, instead of doing it this way, we can just kind of leave the c out of the problem. Let's just kind of, well, I can erase it, I guess. And then later on, after we've done this, we could do a plus c. So Rosa, I think, is thinking we can do, okay, it's y equals e to the 7x plus c, like that. I think Rosa is saying we can add that plus c after we've taken the antiderivative, which makes me think that Rosa is not correct. I'm going to take a look at what the published book answer says. I think Nick is correct. You know, the thing about what's tricky about differential equations is that since c is just a general placeholder that we use for these problems, it doesn't really matter. Much of part G of oh yeah, we're going to talk about this during the lesson. Nick is correct and Rosa is incorrect. One thing that's interesting about the plus c situation is that there are a lot of different ways where you can place it. We generally teach students to do what we did in question B here, is that you stick a plus c right here. After you find the antiderivative, you put a plus c in right there, and then you just deal with it along the way. But although in doing this problem, we ended up taking e to the c and replacing it with another constant, capital C, later on. So c is just a placeholder for a constant you don't know yet, and you can generally swap out an operation involving c for another c because you don't know what it is, and it doesn't really matter. Sometimes you're given what's called an initial condition, and that would be like a point, like a pair of x, y values that works, and you could use that to back substitute in and solve for c that way. But since we don't know anything, I guess my short answer to this question is that Nick is correct. You have to do it right after you find the antiderivative. You have to do it then. Otherwise, it doesn't balance out. And we will see that today in class in question G anyway. We'll take a look at that. It'll be part of our lesson today. So, okay, let's take a look at 7102. This is going to be the one we spend the most time on in this homework video. We're not going to bother doing D because I think it's dumb. And we're only going to look at F for a hot second. But the rest of these are all super fair game. I know I gave you guys a huge circuit training yesterday to do on this, and we're going to do a quiz in class today too, so I don't want to get you burnt out on U substitution too much. Well, the nice thing is the first problem does not require U substitution, so let's talk about question A, which is the integral of, I'm going to pull it up on my other monitor so I don't flip back and forth so much. Question A is the integral of, in parentheses, 3e to the 4x plus 2 to the x power times dx. All we're going to do here is think antiderivatives. We don't need U substitution for this. We're just going to think about what's going to look like. So we know that the antiderivative of e to the x is e to the x, and the 3 is a constant along for the ride. So I know we're at least going to have 3 times e to the 4x in our antiderivative. The only challenge here is if I took the derivative of 3 times e to the 4x, there would be a 4 that would pop out because of the chain rule up here. So I'm going to put an over 4 to catch that 4 that pops out when you take the derivative, and I think that term is done. Very similar is the next term. The derivative of 2 to the x is the natural log of 2 times 2 to the x. So we need to set a trap for that natural log of 2, which is why we're just going to put over natural log of 2 and then put plus c after this. So there is my antiderivative for that first problem. Problem B is going to require u substitution, and it's a definite integral with boundaries, which we haven't talked about in a little bit. What I want you to notice in this problem is that you have sine and cosine, which are popular candidates for u substitution since they are derivatives of each other. Since sine of x is the one being raised to the third power, I'm going to treat that as the u in this problem, and then du is going to be the cosine of x dx, and that gives us a nice one-to-one substitution. Cosine of x dx is right there. Sine of x is the thing being raised to the third power. So our new integral, after we do the substitution, is going to be u to the third power du. However, it would be unwise to leave 0 and pi as the boundaries there. So we need to run those guys through our u substitution. U of 0 is the sine of 0, which is still 0. And u of pi is sine of pi, which is also 0. And so this integral gets to be really easy. It's just going to be 0. Since we're going from the integral from 0 to 0 of something, it does not matter what's inside of that thing. We don't need to evaluate it anymore either, which is pretty cool. It makes that problem really simple. Let's look at question C. I'm going to scroll over to the side a little bit more for this question. (7-102) question C. This is the integral of x squared times 3x to the third plus 5 to the fourth power dx. Again, a really popular candidate for u substitution, since I notice that the derivative of 3x to the third plus 5 will be something times x squared, and I can easily balance that out. This will be 9x squared, like that. Of course, I need to multiply by 1/9. 1/9 du equals x squared dx. I gotta stick a dx on this one too. And so there you go. There's your one-to-one substitution. X squared dx is taken care of. So after our substitution, 1/9 will be in front. We have our u to the fourth power times du. And everything is taken care of there. So let's go ahead and do the antiderivative. This is 1/9 times u to the fifth power over 5 plus c. And the only thing left to do now is to stick our original u back into the problem, right there. So we will have 1/45 times 3x to the third plus 5 to the fifth power plus c. And that will do it. And if you think about it, if you take the derivative of this, that will get you right back to what was originally in here. All of the right traps will be set. The 5 will cancel out with 45 to make 1/9. And that will take care of the 9 that pops out when you take the derivative of 3x to the third. So you'll have just x squared dx left over. Pretty cool. I like when things work out that way. We're not going to do d. We are going to look at e really fast because it's another easy one. E is the integral from e to the third power. I hate that a lot. But it's a pretty simple u substitution problem because it's 1 over x times natural log of x dx. And again, the u is going to be the natural log of x because the derivative of u is 1 over x dx. So you have a really easy one-to-one substitution to do here. Everything is taken care of. So our substitution integral will be the integral of u times du. Literally could not be easier. The only challenge here is the bounds of your integral need to change because we just substituted all the x parts for u parts, and so we can't keep our bounds the same. So we need to think about what is u of e for our bottom boundary. That's the natural log of e, and that is 1. So I'm going to put a 1 down here. We also need to think about what is u of e to the third power. That is the natural log of e to the third power, and that is 3. So I'm going to put a 3 up there. So our boundaries need to change. They used to be e to the third, and now they're 1 to 3. Which is still a pretty easy integral to evaluate because the antiderivative of u is just u squared over 2. Now it's up to you. If you want to plug in your u back in, this could be the natural log of x squared over 2. you can evaluate this from the original boundaries, e to the third to e. Or you could evaluate the integral up top from 3 to 1. I'm going to do the one on top because it's much easier. This will be 3 squared, which is 9 over 2, minus 1 squared, which is 1 over 2, and that's just going to be 4. If you plug in, if you think about it, if you plug in e to the third anyway, you're going to be doing the same math we already did up here, just adding an extra step to your life. So it's kind of up to you how you want to approach it. The answer to this question is 4, though. I'm just going to check that really quick by looking at my answers tab. Just confirming, because I want to make sure I'm giving you guys good information, and I am. Question F, we are just going to look at for a quick second. You do not need to know how to do F for AP Calc AB, but I'm going to talk about it for a minute because I think it's worth mentioning just really fast. It is the integral from 0 to 1 of 1 over the square root of 1 minus x squared. This is one of the inverse trig derivatives. I believe it's the derivative of sine inverse of x. I'm going to really quickly Google that really fast on this one. Let's see. Inverse trig derivatives. It is the derivative of the sine inverse of x. I'm just going to make a note up here. Sine inverse of x. The derivative of that is 1 over the square root of 1 minus x squared. You will not see a question like this on your AP Calc test, and if you do, it'll be like the kind of question that separates you from 4 from a 5. It's not going to be one of those. So what we are meant to see here is that this is the derivative, the integral of, the antiderivative of this is sine inverse of x. Evaluated from 1 to 0 is really what this is. That's all we're meant to see here. No fancy U substitution necessary. It only requires you to recognize that structure. If you're a memorizer, you might already have recognized that as one of these. Maybe you can go through the trouble of thinking about, okay, this is 1 and this is the square root of 1 minus x squared, something like that. You could think about things like this. Sine inverse of 1 is which angle has a sine of 1? That's pi over 2. And sine inverse of 0 is 0, so the answer is pi over 2. You do not need to do this problem for credit, but I figured I'd show it to you anyway just as a heads up, because it showed up on the circuit training yesterday also. 7103 is an easy question to answer. Population growth. This is just really wrapping your head around an idea we're talking about in class today. Population growth is proportional to the current population. For example, if a town has 100 people, its change in population for a year will be based on those 100 people. Therefore, its change will be much smaller than that of a large city like San Francisco with 800,000 people. Why? And write down your reasoning. Here's the thing. We tend to think of percent growth. We tend to think about percentage growth being equal. Like, if Kalkaska is growing by 2% and San Francisco is growing by 2%, well, they're both growing by 2%. But because the base number of people living in those two towns is vastly different, the actual number of people that we're talking about is going to be way different. And that's what's really at the heart of what we're doing in class these next few days. Percentage growth depends on how many people you have there, because the change, the dBdt we're going to talk about in class, the change in population with respect to time, that's going to depend on how many people you have. Depends on current population. And we're usually not used to thinking about it that way, but that's going to be the thing we got to think about. So it's proportional to your current population. Proportional means that there is some sort of constant times dPdt happening right there. That's what we're thinking about. Okay, let's look ahead at 104. The wedding cake part 3. We've looked at this problem on a number of different homework problems. So Kiki is still trying to decide the shape for wedding cake, and now she's considering 16 layers. If you think about this problem, we've done 4 layers and we've done 8 layers, and now we're going to think about 16 layers. The largest diameter is 16. Each subsequent diameter would decrease by 1 inch. Each layer of this cake would be only 1 inch tall. Normally, we don't do the Riemann sum, but I'm going to set it up for you because I really just want you to think about this, because this is a visual thing you got to wrap your head around for the last section of AP Calc AB. So again, our cake looks kind of like this. You have different subsequent rings. Each layer is getting a little smaller, and they're all stacked on top of each other, kind of like this. Just trying to draw to the best of my ability what this would look like. Something like this. That's what's happening there. Now we have each layer is a cylinder, and the cylinder's volume is equal to pi times the radius squared times the height. So we need to think about the volume of each one of these things. The biggest one has a diameter of 16, which is a radius of 8. So our biggest one, let's say our first one, is going to be pi times, they're still 1 inch tall. It's going to be pi times 8 squared times 1. That's the first one. Now the next one, this time we're getting smaller by, the diameter decreases by 1 inch, so the radius is decreasing by half of an inch. So the next one is going to be pi times 7.5 times 1 squared, sorry. The next one is going to be pi times 7 squared times 1. And so on, and so on, and so on. 6.5 squared times 1. Now, we could keep this going all the way. We're going to have 16 different layers. I don't want to write 16 of these things. So we're going to cleverly use a sigma to talk about this answer. We're going to cleverly set up a summation to help express this situation here. That's the idea. We're adding up all of these layers. Each one is just a cylinder with a pretty predictable volume. So, first of all, I want you to notice that each one of these things has a pi involved. Pi times 1, technically. And then we're just multiplying by 8 squared plus 7.5 squared plus 7 squared plus 6.5 squared plus 6 squared plus 5.5 squared, so on, all the way down to 0.5 squared, because I believe the smallest one is going to have a diameter of 1 inch. I think that's right. So what we need is a way to express this. So first of all, the constant of pi is going to hang out in front of our sigma. Now we're going to have 16 layers to this cake. So we're going to go from I equals, you could do I equals 1 to 16, but we're going to go from 0 to 15 here. Really just got to think about each one of these layers. And each layer is going to start with the original 8-inch diameter and subtract whatever I you're currently on, and then square that. I think that's how this is going to work. If you think about that program, that should work. Because the first one is I equals 0, and that will be your 8. The next one is I equals 1. Oh, sorry. I don't want to subtract the full thing. I want to subtract 0.5 I. There we go. Because if I is 1, then now I'm going to subtract 0.5, and that gives me 7.5. If I is 2, now I'm subtracting 1, and that gives me 7. If I is 3, I'm subtracting 1.5, and that gives me 6.5, and so on, and so on, and so on, all the way down. I think this works really nicely. Now, we could crank this out on the calculator by hand manually, but let's just let this calculator do all the calculation for us. Let's go ahead and open up. We haven't opened up sigma in a while. It's going to be the summation notation in alpha F2. Boom, right there. We're going from x equals 0 to 15 of 8 minus 0.5x. And, I'm going to go all the way back over here. I'm going to push second insert, and I'm going to put a pi in front of that thing. There we go. This should do it. Oh, we got to put a square at the end of this, too. There we go. That should do it. I wonder if that's going to square the whole thing, or if it's just going to square what I need it to be. That's not going to be correct. Hang on, I got it. Because that, no, I think I'm squaring the entire thing there. There we go. I want to square this. Nope, not you. Oops, shoot. Shoot. You guys are having fun watching this video. Watch me struggle with my calculator. It's fun. What if I square this inside? There we go. That's what I want. That's what I want to do. Okay. There we go. That's the answer I'm looking for. It's about 1174.955. This problem will likely show up in Chapter 7 or Chapter 8, and the very last thing we do. We are only doing the first section of Chapter 8. So we have 2 weeks or 2.5 weeks left before you guys are ready to rock, and so we're going to finish up Chapter 7. This is the last section of Chapter 7 we're doing, and one more section of Chapter 8, and then we're done. This is inches cubed, by the way. Units there. Okay. Let's look at an easy question, 105. We're going to answer this in 5 seconds. Simplifying these exponential expressions. Try without a calculator first. Honestly, these are just testing your logarithmic knowledge. E to the natural log cancels out, leaving just the 11. And same thing, natural log of E cancels out, leaving just the 4. Same thing with B and C. They're the same thing. This is just going to be E. And in question D, the 10 and the log base 10 cancel out, leaving just the x. So this is just refreshing you on your knowledge of how logarithms balance each other out and cancel things out. So there you go. And we finally have a multiple choice question, which is, I wish this curriculum had more of these in our textbook, because we talk about them all the time. They're a big part of your AP test. The average value of that function on the interval from -1 to 1 is nearest to which one of these? Because of the decimal nature of this question, this would be a calculator active question on your test. So all you need to know is how to find the average value of a function on an interval. And that's pretty easy to do. Our a is -1 and our b is +1. And so the formula is 1 over b minus a times the integral from a to b of your function, f of x dx. Like that. It's pretty intuitive. So in this case, we're going to go 1 over 2, since 1 minus -1 will be 2. And we're going to multiply that times the integral from -1 to 1 of our function e to the sine of x squared dx. Could we be reasonably expected to evaluate this integral by hand? Sure, but who cares? We're going to let the calculator handle it, since they gave us, if you see decimal multiple choice questions, you use your calculator. Don't try to do things by hand. We're going to put a 1/2 in front of this thing. Oops, I got to put a 2 there. Times alpha f2, fn int, -1 to 1. We're going to very carefully program this in. This is e raised to the sine of x squared power close, and then we go times dx. And this should do it. Looking like 1.414, which is really close to the square root of 2. Really close, but not exactly there. So I was thinking this might be something nice, but which one is that? This is about 1.41, 414. That is E. Wrap it up, do. Cool, 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 cool. Hey, we got out of here in under 30 minutes, which is the nice thing today too. You guys are awesome. Keep it up. Believe in yourself. You can do this. This is not only is it within you, it's beyond you. You are beyond it. That's what I meant to say. I'm trying to be positive here. Give me a chance. Okay. You guys are doing great. I'll see you in the next video.